Okay, now we will start optics. This is our last chapter. But optics has two separate chapters. One is called geometrical optics or ray optics. Other is called physical optics or wave optics. First, we will study the ray optics. It considers the rectilinear propagation of light, and here we consider the wave nature of light. We can explain reflection, refraction, dispersion with ray optics, but with wave optics we can explain everything. Reflection, refraction, dispersion, interference, diffraction, polarization. So laws of ray optics can be generated using laws of wave optics. Here basically we are considering some approximation that light is moving in a straight line. Light is moving in straight line, which is called rectilinear propagation of light. Okay. So whenever a light just separating it. Okay. So whenever we have a interface of two medium means two junction. It is the junction of two medium, optically transparent medium, Sorry. Sorry for the interruption. So interface of two medium means it is a junction of two optically transparent medium whose optical densities are different. Now we get another term, optical density. It depends on the speed of light in a specific medium. Now, if the speed of light is greater, then the medium is optically rarer. Now, on the other hand, if the speed of light is less, the medium is optically denser. So this optical density is not uh, like the mass density, okay? It is different from the mass density. It depends on the speed of light, and in further course we will see it depends on basically the refractive index of the medium, okay? Now, whenever a light wave incident on the interface of two medium, then a portion, this is incident light, this is medium 1, this is medium 2, a portion will be reflected from the point of incidence. So it is called a portion will be transmitted, but in a different direction. That is called refracted ray. And also a third portion which will be absorbed. So there are three portions of the incident ray. One is reflection, refraction, and absorbance. So a part of the incident ray will be reflected into the first medium. A part will be transmitted into the second medium, but in a different direction, refraction, and also a part will be absorbed into the medium. Now, first consider the reflection of light. There are two laws of reflection. Do you know that laws? Shomallo, do you know the laws of reflection?
Laws of reflection. That formulated one.
There are two laws of reflection. Do you know the
Mhm.
laws? Yeah.
Um,
This is called normal. Okay. This
yeah,
one.
yeah, that angle between incident and yeah,
The
and
angle the incident ray
reflected
made
rays
with the normal at the point of incident, that is called
is
reflection, angle of reflection. And the angle the
hmm,
reflected ray makes with the angle normal at the point of incidence is called angle of refraction. Now these two angles are equal. These two angles are equal. Angle of incidence is equals to angle of reflection. And second law is the incident ray reflected ray and the normal at the point of incidence
yes,
are at the same plane,
hmm,
are at the same plane. Okay. Now we have learned about reflection at plane surfaces in our lower classes. So the syllabus does not include the reflection at the plane surfaces. Here we will start our study with the reflection at spherical surfaces. That means spherical mirrors. So what is a spherical mirror? A spherical mirror is a reflecting surface A spherical mirror is a reflecting surface which forms part of a hollow sphere. So if the mirror can be considered as a part of a hollow sphere, then the mirror is called spherical mirror. So just consider a glass sphere, hollow glass sphere with center at C. If we cut this portion AB, then this portion APB can be considered as a spherical mirror. Now, we can either silver the inner portion or the outer portion, according to which we can have two types of spherical mirrors. If the outer portion is silvered, then it is the reflecting surface. On the other hand, if the inner portion is silvered, then it is the reflecting surface. So this is known as concave mirror, and this is known as convex mirror. Reflecting, when the reflecting surface is a convex surface, then the mirror is convex mirror. If the reflecting surface is a concave one, then the mirror is termed as concave mirror. Okay. Now we will define few things with the aid of this figure. First, pole. Here P is the pole. It is the middle point of the spherical mirror. Middle point of the spherical mirror. In the figure, it is P. It is called pole of the mirror. Middle point of the spherical mirror is called pole of the mirror. Secondly, center of curvature. C. The center of the sphere of which the mirror is a part is called center of curvature. So here C is the center of curvature. Next, radius of curvature. R. The radius R equals to here AC equals to BC. This one. So radius again, CP is also same. CP is also same. CP, AC, AC, PC, BC, all are same. Their radius of the sphere of which the mirror is a part. That is called radius of curvature. Then comes principal axis. The straight line joining the pole and center of curvature is called principal axis. So this is radius of curvature and this is principal axis. So what is principal axis? The straight line joining the pole P and center of curvature C is called principal axis of the spherical mirror. Then comes linear aperture. If you cut a portion, so you will get this type of sphere. So the boundary is also circular. So diameter of this boundary, like this AB, is called linear aperture. It is the diameter AB of the circular boundary of the spherical mirror. This is called linear aperture. So this is the diameter. The spherical mirror means you will get this type of mirror. So the boundary of the mirror is also circular. So you will get the diameter of this circular boundary, which is called linear aperture. And this diameter, the angle subtended by the diameter at the center of curvature, this is called angular aperture. So this is linear aperture and this angle is angular aperture. So it is the angle ACB subtended by the boundary of the spherical mirror at its center of curvature. That is called angular aperture. Then I will define more three quantities which are most important in the discussion of spherical mirrors. Principal focus. A narrow beam of light parallel to the principal axis either actually converges in case of concave mirror, they are actually converges, or appears to diverge in case of convex mirror. They appears to diverge from a point F on the principal axis. After reflection from the spherical mirror. This point is called the principal focus of the mirror. Just a minute. So just showing you by drawing figures. This is a concave mirror. This is pole. This is a center of curvature. This is a point F. So the rays which are close to the principal axis and parallel to the principal axis, after reflection from the concave mirror, will pass through a specific point on the principal axis. This F. So this F is the principal focus. Principal focus. Now, in case of concave mirror, this is
The
pole.
principal focus is behind the mirror.
Yes. So when this rays parallel to the principal axis, after reflection, they appears to diverge from this principal focus. Okay. Then comes focal length. It is symbolized by F. So it is the distance between the focus and the pole of the mirror. F is equals to PF. The distance of the principal focus from the pole of the mirror. So this distance, PF, is called the focal length of the mirror. Another very important thing is the focal plane. The vertical plane passing through the principal focus and perpendicular to the principal axis is called focal plane. Now, any parallel ray which are not parallel to principal axis after reflection either actually converges or appears to diverge from any point on this plane. From a point, not any point, from a point, and this point may vary. For different direction of the ray, the point will be different. Okay, just I'm showing by drawing figure. P, F, C. So there is a plane perpendicular, then some rays parallel rays. These rays are parallel to each other, but not parallel to the principal axis. So they will meet at point on the focal plane. So this plane is called focal plane. Or in case of convex mirror, after reflection, they will appear to diverge from a point on the focal plane. So this is called focal plane. Okay, is it understandable?
Yes.
Now, whenever we discuss with this ray optics, we need to follow certain sign convention.
Sign con
Which distance we will
sign
consider positive
convention
and
that
which distance we will consider negative. This is called sign convention. First of
okay.
all the distances are measured from the pole of the mirror. All the distances are measured from the pole of the mirror. That means whatever you want to measure, you have to measure from this P. Clear? Secondly, all distances measured in the direction of the incident ray. All distances measured in the direction of the incident ray are taken as positive. That means in case of concave mirror, when you will measure the focal length or the radius of curvature, you are measuring from P to in this direction. So it is in the direction of the incident ray. So these are positive. Is it clear?
That's behind the ray, behind the
Yeah,
mirror.
behind the mirror. Just you don't care about it is behind the mirror
Hmm.
or in the front side of the mirror. Just see what is the direction of the incident ray,
Yeah.
what is the direction of your measurement. If they are same, then your distances are positive. On the other hand, all distances measured in the opposite direction of the incident ray are taken as negative. So in case of concave mirror, this focal length or radius of curvature, these are all negative because they are measured in the direction which is opposite to the direction of the ray. The direction of the ray is in this way, but we are measuring PF in opposite direction, PC in opposite direction. So they are taken negative. Okay. Is it clear?
Yes.
Fourthly, height. measured upward and perpendicular to the principal axis. Height.
The one is positive.
Yes. Yes.
Above the principal axis, it's positive, and
Positive.
below is negative.
Positive. Yes. Yes. Height measured upward and perpendicular to the principal axis are taken as positive, and height measured downward and perpendicular to the principal axis are taken as negative. So this is a sign convention. Now we will find a relationship between focal length and radius of curvature. See, I will do it for, say, convex mirror. You have to do the same in for concave mirror. I will do it for concave mirror, then you have to do it for convex mirror. All the proofs I will do for one type of mirror. You have to do as homework for the other. Okay. Relation, sorry, between F and R. First, let us consider concave mirror. So any radius is perpendicular to the spherical surface. So here this is I, so this will be R. These two are should be equal. Just a minute. Hold on. So this distance is the focal length F, and this distance is the radius of curvature R. Okay. Now, say this is A, this is B. So angle ABC is equals to angle CBF. Angle ABC is equals to angle CBF by the laws of reflection. Okay. Again, angle ABC is equals to angle BCA because this BCP, sorry, because these two AB and CPA are parallel. So these two angle, this angle and this angle are equal. As AB is parallel to PC, so angle ABC is equals to angle BCP or angle BCF, this angle. So what we got in triangle CFB, this triangle, angle
FBCF equal to angle CBF.
FBC or CBF, this angle is equals to angle BCF. So we can write this CF is equals to BF, CF is equals to BF. Now, if the aperture is small, that means if this curvature is small, then BF is nearly equals to PF. BF and PF are very close to each other.
Yeah.
I'm going to next page, okay? So PC can be written as PF plus FC.
FC.
So what we got? FC equals to BF equals to PF. FC equals to BF equals to PF. Sorry. FC equals to BF equals to PF. Now PC can be written as PF plus FC.
Half of
PF plus FC. Now FC is equals to equal PF. So PF plus PF twice PF. So this is what radius of curvature R, and PF is focal length twice F, or F is equals to R by 2. So this is the relationship between focal length and radius of curvature. Homework. Proof F equals to R by 2 for convex mirror. Now next we will we will find a relationship between object distance, image distance, and focal length, which is called mirror formula. Before going into the mirror formula, we will we need to learn the rules of drawing images, rules of drawing ray diagram.
In class 10, the Most comes, I mean, the best chapter to discuss and to
Yeah,
gain the marks was
I
ray
I
optics
I
only.
I
In
can't
class
can't
10,
hear you properly. In class 10.
yeah, in class 10, the
Yeah.
the highest marks in chapter was from ray optics only because
Okay.
it was totally conceptual wise. The first one.
Mhm.
Before that, we have to all theory wise chapters, uh, magnetic effect that also that did not start. I mean, 12, the level of class 12 as magnetic
Mhm.
effect or magnetism is
Mhm.
whole to part of 12 was.
Yeah.
So we have to just do the theory wise only. So in that case, the reoptics was the best chapter for mark seeking.
Mhm. Here also you will get good marks in ray optics. Okay. So let's start with how we will draw the ray diagrams. We know all the rules, just we will revise them. Both for concave and convex mirror. Any ray which is parallel to the principal axis after reflection should go through the principal focus. Or any ray which is parallel to the principal axis after reflection is appears
Mhm.
to coming from the principal focus. Okay.
From the Prince Focalista.
Just a minute. Hold.
And another one was
Now, secondly, if any ray either coming through the principal focus after reflection will become parallel to the principal axis. Or in case of convex mirror, any
will
ray
appear to.
which is directed towards the principal focus after reflection will go parallel to the principal axis.
Then
Parallel to the principal axis.
now we can, yeah, now we can find anything.
Yeah. Now, third rule is any ray which is either passing through the center of curvature after reflection, passing the center of curvature, so it will incident normally on the surface of the mirror, so it will just reverse back.
Yeah,
It will just
bounce
reverse
back.
back,
Yeah,
bounce back, reverse back. In case of concave convex mirror, any ray which is directed towards center of curvature, after reflection just retrace its path. Okay. So these three are the rules for drawing ray diagram. Now, on the basis of these rules, now we will try to draw ray diagram, try to find where the images will be obtained when the objects are at different places. Okay.
Yeah. And these three lines where they cut each other, I mean, from the point, I mean, object distance and the
Yeah.
object
I'm,
height
I'm
and the mirror height, they cut it. Yeah.
everything. I'm just going.
Yes.
So, image formation. First, we will do it with concave mirror. Object placed beyond C. So, what will be the nature of the image? P F C. The object is placed here. OA is the object. So first we will send a ray parallel to the principal axis. It will pass through the principal focus after reflection. And we will send the ray through the principal focus. After reflection, it will become parallel to the principal axis. So these two rays are meeting at this point. So this point is the image of point A. So accordingly, we will get the image of OA as IB is the image of OA. So where the image will be formed? Image will be formed between F and C. Okay. Secondly, it is a real image as the rays are meeting actually, but inverted and diminished in size, smaller than the object. Okay. Now we will now just take the object close to the mirror. So in the next step, we will go on C, then between C and F, then on F, then between P and F. Okay. So second step, object placed at C. Here the object is placed. So we will get a ray. It will pass through like this. And also we will send a ray through the focal point. So it will pass through like this. So here OA is the object, IB is the image. So the image will form at C It is again a real image, but inverted and same size as the object. Okay? Is it okay?
Yeah. Yes.
Then we will place the object between F and C. So here we have placed the object. This is C. OA is the object, and it is meeting at this point. Okay. So IB is the image. So here the image will form beyond C, obviously real image, inverted and larger in size than the object. It will be larger in size than the object. Fourth, object placed at F. This is very interesting.
Yeah.
Basically, it is the most interesting one.
So everything changes. Seem to be.
Yes. So here is the object. If we send a parallel ray, it will pass through the focus. And if we send a ray passing through C, so this is C, it will return back. Here you will get parallel rays. So if we extend in opposite direction, they will meet at infinity, but they will appears to meet at infinity. So here the image will formed at infinity. Now it is virtual image. It is erect. And obviously larger than the object. And last one with concave mirror. This is
Between F
P
and
and F.
O.
P and F. So here we have the object. The parallel ray will pass through like this, and the ray which is appears to coming from C will go in this direction. So these two rays will meet. If we go extend them in opposite direction, they will appear to meet at some point. So this will be the image. So here the image will form behind the mirror at a finite distance. Behind the mirror means
Yeah,
it is
because of the
virtual image. It is erect and larger in size. Now, image formation with convex mirror. We have only one case here. Whenever maybe the object in front of the mirror, whatever may be the position of the object in front of the mirror, you will get an image, obviously virtual image, between
in convex mirror, it's full of virtual.
yes, the image will form behind the mirror between P and F. So it will be virtual image. It is erect and smaller in size. Smaller in size. Okay. So these are the formation of image with different type of mirrors, spherical mirrors, and at different position of the object. Next, mirror formula. The formula is 1 by V plus 1 by U equals to 1 by F, where V is the image distance, U is the object distance, and F is obviously focal length. Now we will do the derivation. I will going into the next page because for the derivation, I need the figure badly. All these derivations in geometrical optics are based on basically geometry. You need very good knowledge on geometry. Okay. So again,
Yeah.
I'm doing it for concave mirror. Consider this is my object AB. We will take three rays. One is parallel to the principal axis, which after reflection will go through focus. Other is going to the center of curvature. After reflection, return back in same path. And next one will hit the pole and it will make same angle. So here A dash B dash is the image. Okay. This is M. This is F. This is C.
Difficulty is
So
also congruency.
FP, sorry, PF is minus F focal length. PB dash is minus V is the image distance. And PB is minus U is the object distance. Okay. CP equals to minus R equals to minus twice F. Okay. Now consider the triangle A dash B dash P, sorry, A dash B dash C and ABC. These two angles are same. These two angles are perpendicular, 90 degrees. So the third angle should be
That's
same.
same.
So they are
Yeah.
similar triangle.
Same.
A dash B dash C is similar to triangle ABC. So ratio of the arm will be same. A dash B dash by AB.
Yeah.
A dash B dash by AB should equals to CB dash by CB. Now we can write this CB dash as PC minus PB dash.
Yeah.
Sorry. CB dash PC minus PB dash.
Then
Okay.
PV.
CB dash is PC minus PB
Yeah.
dash. And CB can be written as PB minus PC.
PP plus
PB minus PC. PB minus PC is CB.
Okay.
Is it clear? Now use the value. What is PC? PC, this is PC basically. PC equals to minus twice F. Okay. PB dash is minus. That means plus V. PB is minus U. And PC is minus plus twice F. Okay. Now again, the triangle ABP and triangle A', are similar because these two angles are same and these two are 90 degree. So the third angle should be same. So triangle ABP is similar to triangle A', So again, ratio of the arm will be same. A', B' by AB should equals to BP, sorry, A', B' by AB. That means PB dash by PB. PB dash is minus PB dash is minus V by minus U. That means V by U. So from these two, 1 and 2, you can write minus twice F plus V minus U plus twice F is equals to U, V by U, or minus twice UF plus UV equals to minus UV plus twice VF, or you can take minus twice UF minus twice VF equals to minus twice UV, or you can write UF plus VF equals to UV. Now divide all through with UVF. You will get 1 by V plus 1 by U equals to 1 by F. Proved. Derive mirror formula for convex mirror. This is also homework. Okay.
That in another term was there that it deals with the ratio of height of object and the image.
Yeah. This is called linear magnification.
N V by N I.
Linear magnification. M, it is equals to the ratio of height of image by height of object. That means HI by HO. Now again, return to the figure. A dash B dash is the height of the image and AB is the height of the object. What we got in the equation 2? A dash B dash by AB is equals to V by U. HI by HO is A dash B dash by AB, which is equals to V by U. So linear magnification is also the ratio of the object distance to the image distance. Okay. Now there are several use of this convex mirror. Just go through that portions and also the problems. Okay. So this reflection at spherical surface is completed. In the next class, we will start with
Yeah.
refraction of light. Okay. So that's all for today.
Okay.
Thank you.
Sir, does
Yeah.
okay, sir, optical density deals with yeah, optical density indeed. I mean, in simple word, it deals with the free space in a certain medium.
Repeat.
I mean, light need a space to travel. So
Yeah.
optical
Light,
density
light do not need
deals with
any
free,
medium to
free
travel.
space.
First consider that light do not need any
Yeah.
medium to travel. Okay. Now, if there is any medium, it may
No.
provide some resistance to the flow of light. Okay. So in different medium, velocity of
Yeah.
light is different.
No. I'm here. Hmm.
So on the
Yes.
basis of velocity of light, we have defined a term which is called optical density of the medium. If the optical density is, if
Okay.
the velocity of
Hmm.
light is less in some medium, we are saying that optical density of the medium is greater. If light is moving faster in a medium, we are
Hmm.
saying optical density of the medium is low. Okay.
Yeah. Yeah. Mhm.
Anything more? Anything else?
Yes, sir.
Do you know
No,
anything
sir.
else? Okay. Thank you. So I'm just switching off.
Okay.
Our next class will be
Okay,
on
sir.
Saturday at same time.